Okay, so what I want to do today first is sort of step back a little bit on what we were doing for last 2 weeks, right? So the topic that we've been looking at for last 2 weeks is what we call unsupervised learning. And what I sort of mentioned early on is that one primary way to look at unsupervised learning methods is what we call latent variable models. So most of the unsupervised learning methods can be posed as this. Well, not all of them, but a lot of them, right? Anything that has. So this is a very probabilistic sort of approach. So if you do not have probabilities, then things will be a little different. But the idea behind these LVM models is that you observe some X, right? And so far we have been looking at X as some vector of observations, but this could be something else. It could be text, it could be strings, whatever, right? So you observe some X, but instead of directly modeling the probability distribution for X, what we typically do is we model the probability distribution for X given some latent variable Z and some theta, which are the parameters of your model, right? So, and we also have a distribution for Z, right? So in the generative form, the way this sort of looks like is that how the data is generated is through a two-step process. You first sample Z from this, right? From this distribution, and then use that to sample X. And the problem, the machine learning problem, is that we would only be given X, right? So we will be given just some training data, which will be a bunch of X's, and then we need to figure out what are the theta, the parameters of our model, and also what would be the most likely Z. So eventually what we would like is what is Z, what is theta, which is the learning part, and then what is PZ given some X, right? So this is the inference part. Then what we did was we saw that clustering, right? Clustering could be thought of as a latent variable, as an instantiation of latent variable models, right? Because in clustering, we are interested in some hidden quantity, which is the cluster index. So Z kind of denotes which cluster X belongs to. But in clustering, we do not have an explicit sort of probability model. But the philosophy is the same, right? And then we also saw that if we treat Z, right, if Z is categorical, which means it takes 1 out of k values, then latent variable models become mixture models, where Z indicates which mixture component data is coming from, right? And then we saw that k-means clustering. Well, that's it. So mixture models, right? Then the question becomes, how do we learn the parameters of this mixture model? We looked at one algorithm called expectation maximization. So this is just sort of a quick review of what we have done so far. So, or EM. So this optimization algorithm, which lets you the joint or the marginalized likelihood of X given theta, right, over all possible values of Z. And if you look up our discussion in past couple of classes, we have discussed why this is important, right? And then we saw that one version of EM, which we call hard EM, is what k-means does. So k-means clustering is a clustering algorithm, right, that's been proposed to clustering problem. But EM, if you sort of put some constraints on EM, which means essentially what you're saying is that at your E step, you force your objects to belong to one Z. So you just one PZ given X comma theta will be 1, everything else will be 0, right? So then that becomes k-means clustering, right? Then what we also saw was that if Z, instead of being categorical, if Z belongs to RL, which means Z is a vector of L numeric values, right? Then what we get is what we call factor analysis. And this is what we did in last class, right? Factor analysis. And then we saw, for a special case of factor analysis where everything is Gaussian, we saw how to find Px given Z. We found how to figure out this Pz given X, right? So everything was nice and Gaussian because of the nice properties of a Gaussian distribution, right? And then I also kind of mentioned that if you want to estimate the parameters for a factor analysis, you can use expectation maximization there as well. We didn't go through that algorithm. You'll have to derive it yourself, but you could, in principle, apply it. All right. So this is where we were. Right. So just a quick review of what factor analysis was. So here, what we assumed was that z, right, the hidden variable, is coming from a normal distribution with some initial mean and covariance. In fact, for most factor analysis models, we assume this is 0 and this is just an identity matrix. Okay, and then what we say is that px given z comma theta is also a normal distribution, right, with mean as wz plus mu and covariance matrix as a psi, right? And typically we assume that psi is diagonal. So this was the setup for factor analysis. So we have done this in last class, right? So I hope you sort of know what I'm talking about here. Now in the end, what I did was so of course, and then we looked at some examples, and basically the effect of this model is that it lets you understand some hidden dimension. So it's kind of like a dimensionality reduction method where you're given some x, right? But you can, if you knew what w and psi and mu were, which are the parameters of the model, which you can get from EM, then you can find pz given x comma theta, right? Just by applying Bayes' rule, and it turns out that's also a Gaussian, right? So what does this mean? This means that if I give you x, some data point x, which is in d dimensions, I can get what will z be. Actually, I'll get a distribution over z. Typically, we just work with the mean value of that z, right? So it lets, and so x belongs to Rd, right? It's a d-dimensional space, and z belongs to Rl, and typically we assume that L is less than d or much less than d. So this is what lets us do dimensionality reduction, because it allows us, even though our original data was in d-dimensional space, it lets us represent it into a smaller dimensional space. But factor analysis was not proposed as a dimensionality reduction method. It was more proposed to understand what are the latent variables. So in factor analysis, we don't actually worry about this as much as what we worry about W, because W is that latent loading matrix, right? So W tells us how are the features that you observe sort of connected with each other. So the idea is that maybe you are looking at data which is in 12-dimensional space, but 6 of those features actually are very similar, right? And 6 of them are different, are similar among each other. So factor analysis, this W matrix will tell you, okay, these 6 are together, these 6 are together, right? So they kind of tell you what are the hidden factors that actually generate the data. So it's used a lot when you're dealing with things like psychometrics, where you go and take a survey of people. You're trying to understand behavior of people. You take a survey which has 300 questions, let's say, right? Not all the questions are sort of independent of each other. So factor analysis kind of lets you extract those features. Those hidden factors, right? So that is the idea. But in the end, what I also mentioned was that but you could use this for dimensionality reduction, right? Nobody's stopping you for that. So if this psi matrix is just sigma square times I. So let's say this psi matrix is still a diagonal matrix, but each entry is the same, right? If this happens, then this factor analysis actually is same as what we call probabilistic principal component analysis, or PPCA. Okay, so PCA, some of you might be familiar with that, but we are going to look at PCA today. PCA was an explicit method meant for dimensionality reduction. Okay, given data in d-dimensional space, the purpose of PCA is to find smaller dimensions such that when you convert the data into small dimensions, it retains most information, right? So it retains the information. So that's what PCA does. But it turns out, and PCA had no probabilities associated with it, right? So PCA does more like a spectral decomposition and everything. So, but if you look at analysis, then PCA and factor analysis are similar, and that PCA is called probabilistic PCA, right? So that is another thing we also assume here is that, see, here we are not making any assumptions about W, right? W, which is a loading matrix, it's just some loading matrix. So what is W? So W is a D cross L matrix, right? Because we multiply W with Z, right? And that gives us a D cross 1 vector. So the effect of W is that when I multiply WZ, it gives me some X, right? Or the mean of X, which means that essentially it is converting an L-dimensional vector into a D-dimensional vector. So think of this W. So Z has some features associated with it, right? So Z would be a column vector with L features, Z1, ZL. And what you need is X, which has D, X1 through D features, right? That W is a D cross L, so it's D cross L. So to get this entry, the first entry, what you do is you take the first row of W and multiply or take an inner product with this, right? So you can think of this as a transformation of your original vector into a one-dimensional value. Same way the second one will do with the second row and third row. So each row of this W can be thought of as a way of transforming your data, right? So each row, if you look at the values in this row, they will tell you what values of this hidden variable do they like, right? So if some of these are 0, then they are not sort of using this. So this tells you how much of these factors are loaded to get your X. So that's why we call it a loading matrix, right? But when you solve the E factor analysis and get a W, there is no special structure to W. But if we force, if this and if W is orthonormal, if we force W to be orthonormal, what does that mean? It means that if I take every column of W and take an inner product with any other column of W, it will give me a 0 value. And if I take its inner product with itself, then it will give me a unit value. So which means that W transpose W, or WW transpose, because it's symmetric, is identity. So if this is true, then it's called principal component analysis. The reason we want it to be orthonormal is that when we are doing true dimensionality reduction, right, what that means is that the dimension, the new space in which you are transforming your weights or your features should also be orthogonal to each other, right? Because if you think in geometry sense, when we represent a point in a 2D space, when you say this is X, this is Y, we assume that X and Y are orthogonal to each other, right? In three-dimensional space, we assume X, Y, Z are orthogonal to each other. Now, if I transform this into a new space, let's say I just want to transform a two-dimensional coordinate system into another two-dimensional coordinate system, which is maybe just rotated, right? If you want it to be a true coordinate system, the new axes should also be orthogonal to each other, right? Because that is the property of a coordinate system, that all of the basis vectors that represent your coordinate system should be orthogonal to each other, right? So that is why for a true dimensionality reduction, we want it to be orthogonal to each other. So we force W to be orthonormal. So you can still solve a EM to do this factor analysis with this as a constraint and get the answer. And that is what we call probabilistic PCA, or probabilistic principal component analysis. But today we are going to look at just the principal component analysis, the way it was originally proposed in 1901. And then we'll see the connection between that and PPCA as well. All right, any questions so far? Yes, go ahead. Right. Okay, so it's a good, right. So that's a good question. So the question is, how do I determine this L, right? So this L is again the same story, right? It is a hyperparameter of this. So this typically comes from some domain expertise. They tell you that, okay, so going back to that survey example, right? So let's say you have collected this data, which is, each data point is essentially responses to 300 survey questions. And let's say you're trying to model the personality traits of people. then maybe some psychologist could tell you that, typically there are 5 personality traits. So then you use it as 5. But there's, again, no good way of estimating this. So I have sort of used factor analysis to study countries in the past, right? So I've looked at data from CIA World Factbook, where every country has many parameters. Then some domain expert, somebody told me that, a country has 3 basic factors: economy, demographics, and there's one more I forgot, natural resources, right? So then I said, okay, then that means that I should look for 3 factors. So something like that. All right, any other questions? Okay, so let's move to principal component analysis. Right. So we looked at this, right? So let's introduce PCA, right? So let's say I have these 5 data points represented in a 2-dimensional space, right? And what I want to do is I want to embed them in 1 dimension, right? Let's say I do not have space to store 5 times 2 values, because everything will have 2 coordinates. I just have space to store 5 values, which means that I want to embed it into 1 dimension. So how can I do that, right? So I can do it many ways. For example, I could just store their x-axis values, right? So I can just store 0.2, 3, 0.5, 0.65, and 0.7. That's one way. Another way is I could just store their y-axis values, right? So those are 2 ways to represent data. But what is the best way, right? So the first question is, how do you measure this best thing, right? So what has been shown, now this is a result more from statistics and information theory, is that if you find a direction, so essentially what you want to find is a line on which you can project your data, right? So for example, earlier I said I want to put it in 1-dimensional space along x-axis. That means that I draw a line like this, and then I project everything on that, right? So that is one way. Another way is on the y-axis. But what we really want, so this is my data. So I want to draw a line, any line, and then I want to project all of my data points into this line. So this will be the first point, second point, third point, 4.5 point, right? So we know geometrically how to do this projection. So what we want to find is, what is the best line such that the points are as far apart from each other as possible, right? So that is the point. So for example, if I draw another line, let's say just a line along the x-axis, and I project my points, so the points would be here, 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 and here, right? So that's one way. If I put it on y-axis, it will be like this, and then along this line like this, and I can draw any arbitrary line, and I can project data onto that. So our task is to find the line that gives us the best separation between the data. So because if you think about dimensionality reduction, when you do dimensionality reduction, you lose information, right? Because earlier your data was in 2-dimensional space. Now you want to represent it in 1-dimensional space. Clearly there will be some loss of information. You want to minimize that loss, okay? So that is the point. So what has been agreed upon is that the best line would be one which maximizes the variance of the projected data, all right? So whatever data that you get after doing this projection, you want to make sure that the variance is maximal, because, because that will give you the best separation between the data points, right? Because in the original space, data points are very nicely separated. You want 1-dimensional thing in which the data is again nicely separated, right? So for example, let me take another contrived example. Let's say your data was like this. Okay? Now, if I project my points on the y-axis, then they will look like this. If I projected it on x-axis, they will look like this. If I project them on a line which is actually this line, I'm assuming all the points are on this line, then they will look exactly like what they are, right? So if you compute the variance of these possible projections, you'll see that this variance is the largest. Right? Variance is just sort of x minus mean and x minus the mean square of that, right? So how do we find this line? In this contrived example, of course, there was a line that you could have fitted, so that's fine. But in general, when you have data in any higher dimensional space, how do we find a sort of an embedding which maximizes the variance? All right. So that is sort of what PCA does. Okay? So the principle behind PCA, the driving principle, is that you want to find the direction in which you lose least information, and you quantify that loss of information by saying, I want to maximize the variance. So if I maximize the variance, I will lose the least amount of information. Right? So the question becomes, okay, how do we find this direction of maximal variance? So we can actually do it simply by doing a little bit of mathematical optimization, which clearly we love. So here's the idea, right? So let's say we don't know what the direction is, right? So we'll say let U, this is a unit vector with unit magnitude, denote the direction of our line, that line on which I want to project things, right? And what I want to do is, first I want to compute what is the projection, right? So if I have any data point, xi, then if I compute xi transpose u, that will give me the projection. So if I want to find where does it lie on this line, then xi transpose u will give me that, right? So this is just geometry, right? So the idea is that if I have any line, so basically what does this vector indicate? This is actually a perpendicular vector to the line that we want to project our data on. So if I have a point and I want to see where does it lie on this line, I just put inner product between the line and this thing, right? So that is this is the new point. So this is the embedding, right? So let's call it Zi. What we want to do is we want to maximize the variance, all right? And now in this whole discussion, what I'm going to assume is that all of our data has zero mean, okay? So mean-centered data. So if your data is not mean-centered, you can make it mean-centered. So let's say this is my data matrix. So all of my xi's are here, x1 transpose, x2 transpose, and so on. So if this data is not mean-centered, you can just take a column mean and subtract it from every vector. That will give you a mean-centered data. So let's right now agree that our data is mean-centered, right? So it's zero mean, which means that if I want to compute the variance, right? So variance of my embedded data is going to be so it will be Zi transpose Zi, right? Summation 1 over n I equal to 1 through n. Actually, sorry, Zi is actually going to be a number, right? So we can just say Zi square. So this is just the formula of variance. This is I mean, it could be n minus 1, that doesn't really matter. But here we are assuming it is 1 over n Zi square. That's assuming that the mean is 0, right? So this is easy. And that can be written as, I'm going to replace this with this. So it's xi transpose square, right? And if I open it up and write it together, it will look like this. 1 over n summation all right, and of course this is I equal to 1 through n, because you're computing the variance of your entire data set, and you can see that these parts do not have I, so I'll bring them out. It will be u hat transpose u hat, right? Now what you will see is that this is nothing but the, or actually no. Assuming, now remember that we have assumed that our data is mean-centered, right? Which means that this is nothing but the sample covariance of my original data set. Because typically sample covariance is written as this. It is xi minus mu xi minus mu transpose. No, why did I say, right? 1 over n for all I, right? And since we are assuming that mu is 0, so then that becomes exactly this, right? So I'm going to write this as S, a matrix S. So this is our sample covariance matrix S. So what we want to do is, if we want to find the U that gives us the embedding with maximum variance, basically you want to find a U that maximizes this, right? Plus, we also want U, so you can an optimization problem, right? To find U with maximal variance, we want to maximize this. Find argmax of U such that this thing is maximized, right? Subject to, there is a constraint there, subject to a constraint that U transpose U is 1, because it needs to be a unit vector, right? So, because if you just maximize this value, then you can arbitrarily have U as all infinities and that will maximize this whole thing, right? But you want the U to be a unit vector which maximizes this quantity, all right? So this is actually easy to solve because you can introduce our favorite Lagrangian multiplier method. This is a constraint optimization problem with an equality constraint, which means that I can solve another problem which is UTU, right, plus lambda equal to 0, right? So this is easy. Any questions so far? Right. So let's see what this gives us. This actually gives us a very interesting result. So I can do two things. First, I'll compute the partial derivative not equal to 0. So we want to find the maximum value for this, right? So the first thing I'll do is I'll compute d by du of this whole thing and set that to 0. Right, which means that you'll get 2us or 2su plus 2 lambda u, right? This is just the derivative of this is su. This is something that you'll get from the matrix cookbook as well. Plus 2 lambda u is equal to 0, right? Implies that su is equal to lambda u, right? And also, if you compute it with this, so then u transpose u is equal to 1 when I compute with respect to d lambda. Right, so these are the two things, right? In fact, I'm going to just switch things a little bit. I'm going to make this minus. That doesn't really matter, right? Because it will be absorbed in lambda. So su equal to lambda u. So this is the equation. So now let's look at this a little carefully, right? So we want to solve this. We want to find the solution for this system, right? S is a matrix. S is a D cross D matrix. This is a D cross 1 vector. So we want to find a solution in which when I multiply S with U, value as some lambda times U, right? So I'm guessing you know where I'm going with this, right? So any guesses? Right. So the solution that you will get for this is simply the eigen decomposition of S, right? Because that is, if you want any U, you can just simply solve the eigen decomposition, right? But the next question is, which eigenvector will I take, right? So actually this will be the eigenvector of S. But if I do an eigen decomposition of S, which is a D cross D matrix, I will get D eigenvectors. So which eigenvector should I choose, right? So I can choose, so let's say I can choose any arbitrary eigenvector, but the variable I will get, and remember to maximize, right? We were maximizing U transpose SU, right? And instead of this, we'll say this is just going to, instead of this, we'll replace it with the eigen decomposition. So that means that objective function value will be U lambda U. So this is transpose, right? Or lambda U transpose U. But because of the constraint, we know that this is just this is unity, right? So this is lambda. So we want to find that, we want to choose that eigenvector in which lambda is, right? So lambda, of course, will be the eigenvalues of your solution, which means that the best embedding will be the eigenvector with largest eigenvalue, because lambda is the eigenvalue, right? When you solve this using eigendecomposition, the eigenvectors will give you U, and lambda will correspond to the eigenvalues, right? So you choose that eigenvalue or choose that eigenvector that gives you the largest eigenvalue. So that will be the direction in which you will, if you want to embed your data along just one direction, right? So choose the eigenvector of the covariance matrix and project data onto that, and choose that eigenvector that has the largest eigenvalue. So that is the idea behind principal component analysis. Now somebody would ask, okay, what if I want to project it in 2 dimensions, not just one? So the answer there is that then you choose the top 2, you choose the 2 eigenvectors that correspond to the top 2 eigenvalues, and so on. If you want to project it in k dimensions, project it in using k eigenvectors. All right? Any questions? All right, so that's sort of easy to understand, not too messy, right? So that is the idea. So the first principal component, or the first direction in which you want to embed the data, is given by the eigenvector with the largest eigenvalue. Second principal component, second largest value, and so on. So you could do that, right? So what that lambda I will give you, that eigenvalue, right? Because you get the eigenvector and you use that to embed your data. That's fine. But there's also this lambda I that comes with it, right? So you can actually use that too. So it turns out that lambda I will actually give you the variance along that principal component, right? Because we computed that just now. So if I use any principal component or any eigenvector to embed my data, then the variance that is given by that principal component is lambda, right? So both things. So when you do your, when you take your covariance matrix, you do the eigenvalue decomposition. Both things are useful for you. You can use the eigenvectors to embed your data, and you can use the lambda to understand how much variance is captured by this direction, right? So the idea is, if you go back here, right? Let's say this was the principal component. This was the first eigenvector. So when you embed the data, then this variance is actually just the lambda associated with that eigenvector, or the eigenvalue associated with that eigenvector. So with this, you can actually compute. So let's say you decide to take the first L top eigenvalues and say, I'm going to take those eigenvectors, and now I'm going to embed my data into this L dimensions, right? So you'll get, instead of D dimensions, L dimensions. So now you can compute this value, which is, and this will tell you what is the percentage variance that you have captured. That kind of tells you how good your embedding is. So if you take all of your eigenvectors, if L is actually D, then you will capture the 100% variance, because you haven't really done any dimensionality reduction. All you have done is that your data was in D dimensions, and you have maybe rotated it a little bit, right? But you haven't reduced the D. So your variance will still be the same. You've captured the whole variance, but of course you haven't gotten any reduction. So the idea is you want to find that L that gives you reduction as well as not too much loss in information. So the variance is sort of analogous to how much information you have lost, right? So that is the idea. Okay, any questions? Yeah. I'm sorry, ask me. if the data points were arranged in a circle. So the question is, the data point were on a circle, would this work? Is that the point? Okay. So, I mean, you can always do this, right? So you can take your data. In fact, I have like an algorithm somewhere, right? So let's say your data was on a circle. So this is the PCA algorithm. So first thing what you do is you mean center it, right? So let's assume that your data was on a unit circle, uniformly sampled. So it will already be mean centered, but you can always do this, right? And then your data will be on a unit circle. Then you can compute the sample covariance matrix, and then you can compute the eigenvectors and eigenvalues, right? So you can do that. The point is that you might not get a good reduction, which means that if you only use the first direction, right, it might only capture half of the variance. And you can actually try it. Later on, I'll show you a notebook where I have the algorithm, so you can try it. Just generate data on a circle and try to fit it. So you can do this, but it might not give you good reduction. Because the point is that see, the principle that PCA works on is that, let's say this was your 2 dimensions, right? That there is some correlation between your 2 dimensions, right? If there is no correlation, if they're both independent of each other, then you cannot do any dimensionality reduction, right? So PCA won't work. There are other methods that could work, because they are on a circle. That means that actually there is some relation between 2 points, but it is not something that PCA could capture, right? So it would be like a failure case for PCA, if you want to consider it like that. Okay. Any other questions? Yeah. Right. Okay, so the question is, why are we doing PCA, right? Because it is giving us a reduction in information. We are doing it for dimensionality reduction. So the point is that even though your data is in d-dimensional space, we do not want to keep it, handle that, because if you remember, like if you did your neural network assignment, right, where you had data in 716 or 784 dimensional space, right? What if, now because the complexity of your algorithm depends on how big that vector is, because your W matrices would be that big. What if you do not have computational resources to do that, right? What if you can only process data which is 10 dimension long? So then you have to do dimensionality reduction, and you would incur some loss, but hopefully it won't be that much, right? So that is one point. Another is if you want to do visualization, because we can only visualize things in 2 or 3 dimensions, right? So if you want to visualize high dimensional data, that's another thing. The third is that goes back to the question that you asked earlier, is that if the data has some dependency between, I mean, if the variables are not correlated, or if the variables are not uncorrelated, they are not independent of each other, then what PCA lets you do is come up with new dimensions which will all be independent of each other, right? So then any algorithm which gets confused by correlated features will perform better in this case. So things like regression that we have seen in the past, right? So if you have correlated variables, regression kind of gets confused, and then typically we do like ridge regression or something to address that part, right? But what you can do is that you could do PCA on your data, right? Reduce the dimensionality, and be assured that you have removed any dependence among the new features, and then your algorithm will work better. In fact, there's one algorithm called partial least principal component regression. It exactly does that. So instead of doing directly regression on your X, it first does PCA, reduces X to a smaller dimensional space, and then does regression. And it has been found that in most practical settings, it actually improves the performance. So PCA might even improve the performance because it removes some of the noisy relationships. All right. So that is the idea. So how do we use PCA for dimensionality reduction? Is pretty easy, right? So first we consider, of course, we do the eigenvalue decomposition of your covariance matrix using your input data. Then we only use the first L columns of your W, right? W is, let's say, the matrix that contains your eigenvectors. So we create a new W matrix in which each column is one eigenvector. We get that. And then when we multiply x with W, now W is d by L, x is n by d. So when I compute this Z matrix, this will be a n by L matrix. So each row there will be the data in this new reduced space. So each input vector is actually replaced by a shorter L by 1 vector. All right, so that is how we work. And it works pretty, and I'll show you some examples, right? So this is sort of the example of a thing. Now what you can actually do is you can also reconstruct your x. So let's say I give you W. Let's say I know what W is, and let's say I give you the Z, which was the lower dimensional embedding. If I multiply W by Z, remember W is D by L, Z is L by 1. So when I multiply W by Z, I will get X again, right? It might not be the same X because we have, of course, lost some information because we have only used the first L eigenvectors in W, which means that your X might not be exactly what your original X was, but it will be pretty close. So if you compute the reconstruction error between your original X's and what your X that you get by doing this process, right? That error is what we call average reconstruction error. And there is a theorem, it's called classical PCA theorem, there's another longer name to it, which says that if PCA will give you the least reconstruction error among any method that you can come up with, which gives you L basis vectors, right? PCA, if you do PCA, which is you start with the covariance matrix, you take the first L eigenvectors, and then you do this kind of reconstruction, PCA will give you a solution that has a minimum reconstruction error. Because think about it, you can construct this W in many ways, right? I constructed it using eigenvalue decomposition, but you can construct this W, which is just L orthogonal unit vectors inside, right? So I can construct it in many other ways. But any way that I choose, I can be assured by this theorem that PCA will give you the least reconstruction error. So that is why PCA is so popular in sort of analysis. All right, any questions so far? Yeah. Yes, so eigenvectors will always be orthogonal, right? So that's the property of eigenvalue decomposition, that you're trying to get vectors that are orthogonal to each other, but they solve that equation, AU equal to lambda U. That is sort of the property of eigenvalue decomposition. Any other questions? Okay, so now let's look at some sort of demonstration which sort of helps you understand this a little more. So here I'm using again sklearn's PCA, but you can always do PCA yourself, right? All you need to do is mean center the data, compute the covariance matrix, do the eigenvalue decomposition. So that's what PCA might do as well. Actually, PCA doesn't do that. PCA does something else which we will discuss in next class, which is singular value decomposition. So let's first look at this example. Let's say this is my toy data, right? This is data in 2-dimension space, and you can see clearly there is some correlation between the two variables. So if I run PCA on it, right? Actually, here I'm actually doing the eigenvalue decomposition. So the output of this is you get 2 eigenvalues and 2 eigenvectors. And you'll see they're orthogonal to each other. Right? So what this is telling me is that since this is the larger eigenvalue, right? So this eigenvector, if I project my data using this eigenvector, the spread in that axis will be the most, and second would be this one. So first let us look at the eigenvectors themselves. So these are the 2 eigenvectors that I get, right? I use just basic plotting to plot these, and since they are orthogonal to each other, so they'll look orthogonal. So basically what they're saying is that project data on this and project data on this, right? So if I do that, this is how it looks, right? So I have scaled my eigenvectors by the eigenvalues. So what this tells me is that I should project this data onto this dimension. If I do this, then I'll get the best spread. If I put it in this dimension, then I'll get a little less spread, right? So that is the idea. But if I project it in both dimensions, then I'm getting no dimensionality reduction. But all I'm doing is, if you think about it, I am rotating my axis, right? So earlier my axis was just my xy, and then because of when I multiply the eigenvectors with those, I'm just rotating it. So even though I'm not really reducing the dimensionality, but at least what I'm doing is I'm making the new features perpendicular to each other. I mean, so there is very less. So if you look at data in this space, in this rotated space, you will see that they are not really correlated with each other, right? So, but of course, what we want really is some kind of dimensionality reduction. So we project it along the first principal component, and this is the spread that we get. And because of the PCA theorem, we can be assured, well, not the PCA theorem, but because PCA explicitly tries to maximize the variance, we can be assured that this will give you the maximal variance, all right? Main thing. All right, any questions so far? Let me do one more example, then we'll resume on Friday. So let's look at the data that we were looking at, the digit data, right? You have grown to love it, I'm assuming. But let's say I load all my 3-digit data set, right? So this is basically a matrix which has all, the dimensionality is, let's see. So it has 613, I'm taking the reduced sample, 613 3-digit images with 784 features, right? So if I look at any image, it looks like this, number 3. So if I do PCA on this, right? So instead of, if I perform PCA, and then look at this plot. Now this plot is very important. Whenever you're doing PCA, this is what we call a scree plot, which tells you how much variance is captured if I use, some number of principal components. So if I use only one principal component, then actually it gives you the ratio. So it kind of tells you, okay, this is the loss that you would incur if you just use one principal component. As you increase the number of principal components, because you can actually have 784 principal components in principle, you'll have 784 eigenvectors, right? So as you increase the number of principal components, and now remember, these principal components are sorted by their eigenvalues, right? So they're not in any random order. So if I keep increasing, the loss that I incur will go down, right? So the idea is to look for a mean here and say, okay, here, if I use, let's say, 50 principal components, then the loss that I incur is not too much, and I get a lot of reduction, right? So instead of representing my data in the whole space until 784, I would be only using data which is 50 dimensional long. So that is sort of the benefit in terms of dimensionality reduction. So let's do this, right? So let's say I take my Z, I take my L to be just 1. So I'm just taking one dimension. And now I transform my data. So instead of taking X, which was in 784, I'm transforming it into one-dimensional space, right? So and then I take any image. So let's say this is one image. So this is the X, and this is the Z, this is the X bar that I get. Remember, we can compute so I do all of this process, right? And then I take the first example and take its Z, and then I reconstruct my X bar, right? So this is the X bar that I get back. So this is the recovery, right? So think about this. This data actually was represented using one feature, the first feature. That's it. So I have reduced my image from a 784 length vector to one value. And then when I recover my image using the W, this is what I get. So it's pretty close, right? It's not too bad, and this is the difference. But the idea is that you use slightly larger values, right? So let's say I take 30. This is what I get, right? Still, you see some difference, right? And if you keep increasing my L, so let's say I take 120, and then I recover, you'll see that now you're getting closer to the image. So even when you're representing your data only in 30-dimensional space, you're able to capture most of the information, and the loss is minimal. And that PCA theorem tells us that any other orthogonal transformation that you could come up with, this difference will be lowest if you did PCA, all right? So if we had done PCA earlier, right, I could have asked you in your neural network assignment to first do PCA, and then you would only work with data which is 30-dimensional long, and you would have done much faster, right? So that is the idea. That is the benefit of doing PCA. So another answer to your question. All right. So next time we'll see how to use PCA for and analyzing faces. Any questions, quick questions? All right, so if you have not submitted your project report, just hand them here, and then I'll see you on Friday. Thank you very much.